Thank you for coming back to the last lecture for the day. And it is a big pleasure to present Gerardo Arizmendi Echegaray from UTLAB, and he's going to speak about bundles associated to even Clifford structures. Thank you, Gerardo. Please go ahead.
Well, first of all, I want to thank the organizers for inviting me here. I remember giving a talk in this conference, I think in 2017, I guess. So it's really nice to come back and also giving this talk live. So also I want to thank Oscar's project for coming here, for his support on coming here. So I will talk today about some bundles associated to even Clifford structures. So maybe even Clifford structures are not really popular, so I will first introduce them. But I will try to focus on the bundles that we have constructed. Also, I want to say that this is a joint work with Rafael Herrera, Paolo Piccini from Universidad La Sapienza Roma, and also from Charles Hatfield. Now he's not in academia anymore. So first I will collect some results that I have done during many years. Well, not many years, probably like 6-7 years. And also there's a disclaimer, this is not that new, but I think it has not been, so I haven't given any talks about this recently. So it's not, so that's why I want to talk about this. So first of all, I will say that, as Pedro was saying, so everybody knows Clifford algebra, or if not, or at least they should, right? So let me just quickly remind you what Clifford algebra is and how does this works. So in general, there's a bigger definition, but the Clifford algebra of Rn with the minus the inner product, the standard inner product, is the algebra generated by the vectors E1 to En, the standard, the canonical basis. With this relation, so this is telling you that EI squared is -1, and that EI times EJ is minus EJ times EI. So that's the relation of the Clifford algebra. So just going quickly, so there's a classification of the Clifford algebra. So for example, if you have just one generator, then E1 squared is -1. So that's the complex numbers. If you have 3 generators, well, actually 2 generators, then EI squared is -1. EJ squared, E1 is minus E1 squared is -1. E2 square is -1, and then E1 times E2 square, you can also check that is -1, so you recover the quaternions. There's a whole list, there's a classification of Clifford algebras. And also I want to talk about a subalgebra that is the even Clifford algebra, and this is nothing else but the subalgebra generated by a product of an even number of elements. So that means, so this is a subalgebra that as a vector space, so one can check that that this Clifford algebra, the Clifford algebra as vector space, not as an algebra, is isomorphic to the exterior algebra of Rn. So then you can identify this as a vector space as the even powers of the exterior algebra of Rn. Okay. So there's also classification. Somehow so the even Clifford algebra of rank R is isomorphic to the Clifford algebra of rank R-1. So you can see that we have like a flip, right? So this is flipped by 1 dimension. So this one is CL1, CL2, CL3, and so on. This is quite standard. And then just to finish the introduction of Clifford algebra, one can identify the spin group. So sorry, there's a typo here. the spin group as the group of multiplications of vectors, and you have to multiply an even number of elements. And then each element here should have norm 1. Okay, you can also identify the Lie algebra of the spin group just as this subspace. Of course, this is in a subspace of lambda 2, the second exterior power of Rn. And this is just a quick introduction to Clifford algebras. Also, you can identify, so this slide is just to tell you that you can see the dimension of the real representation of the Clifford algebra. So they are increasing by 2. Sometimes they don't increase by 2, but so then you have like a periodicity of 8, and then this period after you increase in 8 dimensions. So by this I means that, for example, for R equal 9, then you will have like R, and so the matrices of dimension 16, and this will have so the representation will be of dimension 16, then the next one will be of dimension 32, and so on. Okay, so this is just standard material of Clifford algebras. So then this is the important, this is like the Riemannian definition. This is the important one. And this definition is due to Moroiano and Semmelmann, somehow in the early 2010s. So it's 2010, 2011. So this definition is the definition of an even Clifford structure. They also define Clifford structures, but somehow they are too rigid, and somehow it's better to work with even Clifford structures. So let me just give the definition. So an even Clifford structure is on a Riemannian manifold is a rank R. So you start with a rank R Euclidean bundle. This is like an auxiliary bundle, and then you have a map from the even Clifford algebra of the bundle. So this means you take the even Clifford algebra of the rank R bundle. So this is an Euclidean bundle. So this means you have a metric, and then you have a map here that is called the Clifford map to the endomorphisms of the tangent bundle. And then this is an algebra bundle, an algebra morphism model. And you also want that the second exterior power of the bundle goes to antisymmetric or skew symmetric endomorphism. Okay. So somehow this means that the tangent bundle is a representation of CLR0, and then if you think about the image of EI EJ, then this will be orthogonal local orthogonal complex structures. This is because you have this morphism. There's a remark that I want to tell you. So since this is since the tangent space is a representation space, then this gives you restrictions on the dimension. So for example, if you have R equal 2, then this means like an almost complex structure. So this tells you that the dimension should be a multiple of 2. So then what I want to tell you here is that the dimension will be a multiple of this dr that we saw before, depending on the rank. So for example, we can check things, right? So for example, say rank equal 5, then this should be a multiple of 8. Okay, rank equal 7, this also should be a multiple of 8. And I'm pointing this out because this will appear later. Okay. Anyway, so as I was telling you, rank equal 2, the definition is the same as a complex, enormous complex structure. Actually, it's not an almost complex structure, but it's an almost Hermitian structure. Okay, because the almost complex structure is orthogonal, right? So for article 3, the definition concerns with that almost quaternion Hermitian structure. And this is also one interesting fact that for article 7 and n equal 8, the definition coincides with an 8-dimensional Riemannian manifold with spin 7 as a structure group. Okay. In general, the structure group is C times S. So S denotes the image of spin R inside here. And also C is the centralizer of S inside SON. So one first question is, what's the centralizer, right? What's the centralizer inside SON of this copy of the spin R? Okay. So one result that we did first, we worked with was to compute the centralizers. We did it in terms of Lie algebras. So one can see that depending on the model, mod 8, we have different type of geometry somehow, right? So these are like Riemannians, these are like complex, and these are like hyperbolic, right? Quaternionic, sorry, quaternionic. Anyway, so there's this definition, the definition of an even Clifford and parallel even Clifford structure. So the even Clifford structure is called parallel if there's a metric connection. Sorry, a metric connection, yeah, such that the Clifford map preserves the connection in this sense. Okay. So this implies that the bundle generated by the JIJs, remember the JIJs were the image of the image of the EIJ. So this bundle will be a parallel bundle. So once again to recover the Kahler geometry, quaternion Kahler geometry, and then this case is not spin structures but spin 7 holonomy. So somehow this gives interesting geometries. We also work with automorphism. I will just recall, say what's an automorphism and say the results that we have. So an automorphism is the group of isometries preserving the Clifford structure in this sense, right? So you want that the derivative of the JIs is a combination, a linear combination of the GKs. Anyway, so we have some results about the maximal dimension. So this is our result. These were results that were previously known, given the structure. So you have a manifold, a Riemannian manifold, then the maximal dimension of their isometries is actually this dimension. And then one can see that the classification, one can give a classification of these spaces. We can also do it with almost Hermitian manifolds and almost quaternion Hermitian manifolds. Okay, so we have results involving. So these dimensions coincide with this if you take R equal 2 and 3. Okay. Anyway, so this is one result that we have. We compute the maximal dimension and we saw that they were symmetric and parallel. So that's the classification. So we proved that they were symmetric and parallel, and then there's a classification of parallel even Clifford structures or manifolds with parallel even Clifford structures, and then you can prove that you can see what's the possible cases for each rank. Okay, so I could talk more about that, but I want to focus on the bundles. So this is just a quick summary of what we have done during many years. So then I want to talk about twistors. So first we just saw what was an even Clifford structure, and then I want to say that what we have is like a bundle of almost complex structures. This is a bundle of that satisfies like somehow the Clifford structure, the Clifford relations. Okay. Now we also have this parallelism, and that's why this is important to have the even Clifford structure. So it's not the same having a Clifford structure with a parallel structure. Somehow, if you consider just the even part, this relax the conditions, and it's more. You have more space to work with. That's what I want to say. Now, what I want to focus now is in twistor spaces. So let me just say what we understand as a twistor space. So you start with some Riemannian manifold, and then you have some additional structure. Then you want a fiber bundle over M, such that the fiber is a complex fiber. It's a complex manifold. Okay. So this is important because you want to define an almost complex structure in the total space. That's why you want the fiber to be complex. So it's not that easy to construct twistor spaces if you don't have a complex space. So it doesn't make sense. So what I mean, if you want to construct some, and actually this fiber bundle should be a fiber bundle of local complex structure. So somehow you have the space. So in each point you have the space of all complex structures. So this is a Hermitian symmetric space that is modeled by SON over UN. And then you can try to, given the additional structure of your manifold, try to take some bundles of this big twistor space. Okay, so that's the idea. So how do you construct this complex fiber? Well, it depends on the geometry, right? And then once you have this fiber bundle that have a complex fiber, and also you have this complex fiber of local complex structure, and a connection. So you have a decomposition of the total space into horizontal and vertical space. You can define an almost complex structure in the total space. So that's the magic that you get. So with this ingredient, you can define an almost complex structure in the total space, but it's really important to have this part, okay? Somehow the connection can be given using the Levitic connection and then induce it on the space of normal prisms. But how do you define these almost complex structures? So think about this decomposition. And once you have this decomposition, you can take any vector, any tangent vector to the in a point in the fiber bundle will be have an horizontal and a vertical part. Then the horizontal parts can be identified with the tangent bundle of the manifold. And then since you have a bundle of complex structures, then the point itself is a complex structure on the manifold. So then you can act on it. So that's how this works. And then the other part, the vertical part, you ask in your definition to have a complex fiber. So then this has an almost complex structure, actually a complex structure, and then you can use it in the vertical part. So somehow you have these two parts. So you have a complex structure on the fiber by defining it on the vertical space and on the horizontal space. This is because the fiber is complex. This is because it's a fiber bundle of complex structures in the back. Okay, so this is somehow standard. One important example is the quaternion Hermitian manifold that is part of these even Clifford structures. And then on this quaternion Hermitian manifold, so this means that you have three almost complex structures locally that satisfy the quaternion relations. And then you can take as CP the combination of these three almost complex structures, such that A squared plus B squared plus C squared is equal to 1. And of course, this is just an S2 bundle. And the important thing is that S2 is a complex manifold, right? So the fiber is complex. Okay, that's why this works. And then there's many results well, about this specific twistor space. So this is called the twistor space of a quaternion Kahler manifold. Okay, so it's an S2 bundle. And a classical result of Salomon and Bergerie is that given a quaternion Hermitian manifold, such that this is parallel, so this is the same as a quaternion Kahler manifold. Then for a quaternion Kahler manifold, C, the total space, is a complex manifold. So moreover, if the Ricci, so quaternion Kahler manifolds are Einstein. Okay, so if the Ricci curvature is positive, then zeta is not only complex, but is also a Kahler Einstein manifold. Okay, so this is quite good. So this is quite classical. It's from the 80s. So actually you have more. So there's more geometries involved. So I want to really try to explain this. So this is what is called, what we call the quaternion Kahler diamond. So somehow there's some geometries involved here. So the one that I've just told you is this twistor space. Okay, but there are other bundles that fiber over these quaternion Kahler manifolds. So somehow the work of Swan, Andrew Swan, Boyer and Galiski, and Salomon and Bergerie, they relate. Somehow they realized that they were just some geometries involved. And for example, Boyer and Galiski were trying to study this three-Sasakian manifold. I will talk about what's Sasakian manifold and three-Sasakian manifold. But they were trying to think about Sasakian geometries, and then Sasakian geometries, one can think a Sasakian one like definition of Sasakian geometry is that the cone metric. So you get the cone metric, well, the cone first, and then the cone metric. So the definition would be that actually this is hypercon. So this is one definition. Okay, thinking of what's a three-Sasakian manifold, and then three-Sasakian manifolds, they will have these three vector with some properties on the derivatives. But somehow it makes sense that they have the three vectors. They come from the three. So hypercahler geometry. In hypercahler geometry, you have three complex structures, right? Actually three Kahler structures. So each Kahler geometry gives one vector. So you have these three vectors that satisfy some relations. That's why it makes sense to have three vectors and not just one. One will be a Sasakian manifold. But then there are these somehow fibers that, well, if you think about what I'm telling you here is you have this diagram that corresponds to quaternion Kahler geometry. Quaternion Kahler geometry is for us, for me, is even Clifford, parallel even Clifford structures of rank 3. Okay, so once you see this diagram, once want to generalize, right? So let me ask you, what do you think this will be natural generalizations of these bundles? For example, this is an S2 bundle, this is an S1 bundle, this is an RP3 bundle, this is an H star bundle. So what will be the natural generalization? Okay, so that's what I like these constructions. Okay, so somehow I realized that you can think S2 as a Grossmanian. That's the beauty of this diagram, and that's why I really like this diagram, because at first you don't realize what's the natural generalization. You don't even realize that there's a twistor space. Somehow we were able to construct first this one, and there's theory about the geometries that once you have this space, there's many theories about S1 bundles. What's the geometry? So somehow automatically you get these two geometries, but it's not that obvious that this RP3 becomes like the unitangent bundle of. So actually this SR to the -1 is nothing else but. So you have this. We started, if you remember, we started with this Euclidean bundle, right? So then you can take the sphere. This is an R-1 sphere, so you just take the vectors of R1, and then naturally, given this bundle, you have the unitangent bundles of this sphere, and these fibers over the manifold M. Once we have this construction, the next is what the geometry is involved, right? So that's what we did. We tried to tackle this problem. Given this construction, we tried to see what could we say about the C, what could we say about the S and about the U, but we really work with the C, with the twistor space. Okay. So first, what we did, let me check how many times I have. Okay, I'm okay, I think. So the construction of the twistor space, so we did this construction. So actually, I had this idea of the construction, and then I went to visit Moroyano. I talked to him, and then he told me that some student of him was working on something similar. So we joined ideas, and then we were able to say something more about this construction. So the construction is the following. So a posteriori, it's quite natural, but somehow this took us a lot of time. Well, not a lot of time, but right. But once you know the nice construction, you see that it's very natural, and I really like this construction. So you take. So remember, you have these JIJs, the image of EIJs, and then you just take the linear combination of the JIJs such that they square to minus the identity. Okay, once you have this, the beautiful thing is that you can prove that this is a Riemannian of oriented in planes, and actually this is a complex manifold. Okay, so that's one thing that we realized. So we can work with the geometry of this twistor space. And then just some small remark. So if you think about the Grassmannian in a point, so say you have this point. So then the tangent space is nothing else as this space. So you can see that you have like E1 and then ES. And then this S should be different than 2, and then this S should be different than 1. Okay, so this is the tangent space, and what you can see is that the complex structure is just multiplying by the point. So what do I mean? So if you think about this point, then for example, if this is E1, E3, then you multiply by this with Clifford multiplication, and then you get somehow probably E2, E3. Okay, think about it. Maybe I just, so if you multiply E1, E3, say, of course you have more stuff, right? Let's say you have this one. And then you multiply by E1, E2. Okay, so what you get here, you can commute this one with a -1. So actually you get E2, E3. So this gives you other vector or other tangent vector. You can do the same stuff with this linear combination, and you can see that if you square this operation, you get -1. Okay, so it's a really nice way to see the complex structure of the Grassmannian. I like it, this construction. Anyway, so then once you have the fiber, you can do the same stuff that I told you. It's a natural construction. You in the fiber, you just use the complex structures of the fiber, and in the horizontal space, you just use the fact that this is a complex structure, right? So this is what I'm telling you here. So basically, you split with a connection, you split the tangent space of the whole space, and then here you use the complex structure of the fiber, and here you're just using that the fact that the point is actually a complex structure on the manifold. Okay, what we first proved. So let's just. So we're interested in this structure and see what we can say about if it's complex or whatever. Okay, what's the geometry of the twistor space? So as we said before, a CL30 parallel structure is just quaternion Kahler. So this is done. This is the work of Salomon and Berat Bergeri. So we know that this is Kahler if the Ricci curvature is positive. There's one thing that CL40 structure. So it is well known. Well, it was known by Moroyano and Semmelmann that this is locally a product of quaternion Kahler structures. And remember that somehow spin 4 is the product of spin 3 and spin 3, so you have a splitting. A very nice splitting. Actually, the Grassmannian of two planes in R4 is diffeomorphic to S2 times S2. So actually, this is just the product of quaternion Kahler, and the twistor space also splits. Okay. So we will assume that for now that the rank is greater than 5, and we have a parallel even Clifford structure. That's our setting for now. And then somehow the 8-dimensional case it's treated separately. So remember, we're trying to see what's the geometry of the twistor space. What can we say? Somehow the 8-dimensional case is somehow different. It's not clear why, but some stuff is going in this dimension. So if the dimension is 5, sorry, if the dimension is 8, so the rank cannot be that big, right? Because remember that the dimension increases by 2, it multiplies by 2, so it becomes very big. So either the rank is 5, 6, 7, or 8, and then what you can see is that for R equals 5, this you can identify the fiber, and then so this was studied before by Borstal, and then Borstal said that the twistor space is complex exactly when M is locally symmetric. For R equals 6, so actually you can prove that the manifold is scalar, and so this had also been studied before. And then O'Brien and Rasley. So O'Brien and Rasley had like a very general paper on twistor manifolds, twistor spaces. And then she really considered this before, and then he proved that the twistor space is complex only when the Wagner tensor vanishes. And then for R equals 7, this is the fiber, and actually Borstal also worked with this, and he proved that the twistor space is never complex. And actually, this is one thing that I want to study. So we know that it's not complex, but I want to see what can you say about this space. It's a very interesting case that I'm trying to understand. So for R equal 8, so the manifold is actually there's no condition, and actually the twistor fiber is just isometric to SO8 over U8, and then this bundle is the big bundle, the bundle of almost complex structures on a point. So this is the classical twistor space, the biggest one that you can construct. And there's a classical construction that results that this is so the twistor space is complex only if the manifold is locally conformally flat. So this is really classic. So then what we proved, So after this rank solid dimension 8, we prove that for n equal n different than 8, then the structure is integral. Okay, so we make some computations, nasty computations, I would say. Well, not that bad. I remember this was not that bad. Later on, we prove another stuff that I will talk about, but basically, there's an identity that should be satisfied. So in the paper by so how do we prove this? One knows that this condition should be satisfied for every element in the fiber, and then the idea is in this particular equation that Moroyano and Sentinel have, and somehow you can plug in this E bracket and this commutator, sorry, and then you can plug in all the stuff, and somehow all vanishes. So it's quite nice. So this identity is really somehow help us a lot, and I mean really a lot, because with this identity we could prove that it was complex, but also we also prove that the metric was scalar. There's some and then the metric is scalar only if the Ricci curvature is positive. So again, it's the same as what in Kahler case. So we could generalize these results. That was really nice. And then somehow this was really necessary, the condition, because some constant appeared there, that it's only positive is, so it's only 1/2 is this, so this depends on the Ricci curvature. Anyway, I don't want to get involved in the computations. You can also prove that the manifold admits a nearly Kahler metric. So nearly Kahler metric is less than Kahler. It's some type of almost Hermitian manifold. Yes, and there's one interesting case. The interesting case was due to Frederick, and this is S15. So this is prior to our work. So somehow Frederick studied spin 9 manifolds on dimension 16. He was trying to understand weak holonomy, and in this construction, he tried to construct a a twistor space. Somehow this was one thing that also helped us to construct our twistor space. And it's the same construction. But in this particular case, he was not, there was no even Clifford structures when he was thinking about this, but it's the same definition for this case. And he proved that for this manifold, the twistor space is complex, but it's not Kahler. Okay, so that's quite interesting. Later on, after some years, we were able to add this condition. Sorry. So not only Kahler, but Einstein, and actually it's the same metric. So it was a Kahler Einstein metric. Sorry, and the idea is to use somehow that this was a submersion and using the O'Neill formulas, and then these are really complicated computations. So if we want to reconstruct it today, I have to think about it's really lot of computations. But of course, computing these curvatures and using these equations of Moroyano and Seminal was really important. This is actually essential for the computation. And we really use this part to so. For example, this equation that I showed you before, it doesn't hold for n equal 8. So that's why we couldn't say anything for spin 7, 8, 9. Okay. Anyway, so this relation, this one. this one here only holds, so does not hold for n equal 8. Okay, so that's what we wish we have to work with n equal 8 separately, right? Because this equation does not hold. Okay, and this helps us to prove many stuff. In particular, that is complex, that is Kahler, that is Kahler Einstein. Anyway, so remember, this was the work on quaternion Kahler geometry. What we got. So let me just say something. So in this case, we will have this instead of three-Sasakian geometry, we will have just Sasakian here, Sasakian Einstein. Sasakian Einstein. So once we know that this is Kahler Einstein, the work of Boyer and Galiski tell us that you can have this geometry here as a Sasaki Einstein manifold, and you can also say what's the geometry here. So this will be a Calabi-Yau manifold, but this is just because the work of Boyer and Galiski. So this is what I was telling you. So a Sasaki manifold, so you have this Killing vector field, okay, of length 1, and so somehow this satisfies this relation or this relation, but also it's a result that is the same that this metric is scalar. Okay, somehow once you have this metric is scalar, you can construct this vector, this Killing vector using the Kahler form. Okay. Anyway, so there's a whole dictionary depending on the metric. So the con metric. So this is like the twistor space. This is the C. This is the S, and this is the U. Right here. So once you have some metric here, you can have metric some geometry here and some geometry here. So what we proved, it was that this case, so we were able to prove that it was Kahler Einstein and Pano, and then we automatically got these geometries in the other one. Okay. There's some examples here. Actually, one can make bigger. One can think, so somehow we have this. So our diagram was actually yeah, is this one here? Yes. So this is the tangent space of the sphere. You can also get here the sphere. So this is just the sphere. And this was also so Moroyano also worked with this so the sphere bundle of the rank of the Euclidean bundle. So this is just how this bundle that Moroyano and Semmelman fits into our bigger diagram. Anyway, so that's it for today. So I hope I was not too fast. I hope. So this is just, so first of all, thanks. And then I want to invite you to the 14th mini meeting on differential geometry that Rafael Herrera, Luis Hernandez, and myself were trying to organize. So this will be held on CIMAT between these dates. We haven't decided the dates. This is just tentative, but hopefully this will work, and I want to invite you, and thank you for your attention.
Thank you very much, Gerardo, for the very nice talk, and we'll certainly be at the mini meeting. Are there any questions from the audience here, either here or at Zoom? If not, yeah, so we have a couple of questions.
I have a couple of very silly questions following our tradition of asking silly questions. So when you first defined Z, I thought it was just some sort of a bundle that had that was this complex fibers and also had this property for the elements of each fiber. But then afterwards, it became clear that it was not any bundle that satisfied this, but it was a very specific one, and it even had a name. So is there some sort of uniqueness to this bundle, or is this just one specific one that everybody looks into?
No, okay. So depending on the geometry, one can define a twistor bundle. So that's why I put the ingredient, right?
So a twistor bundle is
yes,
yada yada yada.
So the twistor bundle is the biggest one.
Okay.
So you take all the almost complex structure with an orientation, I have to say. So one orientation, all the complex structures at a point. Sorry, not complex, but Hermitian. So they are orthogonal, and then you get this bundle, right? So this is a big bundle. And then it's already known in dimension 4. If the bundle is complex, then the manifold is half conformally flat, anti-celtual. But in other dimensions, it's known that it's conformally flat. But you can also think about smaller bundles. Okay, so these bundles you constructed with the geometry of the manifold. Okay, for example, you can think about this quaternion Kahler case. So the big bundle will be SON over UN, but the smaller bundle will be S2. Okay, in any dimension, depending on the dimension. So once you fix the rank, this fiber is fixed, and this is quite nice. Even it's not depending on the dimension, as the general bundle of almost complex structures. So I think the generalization is of the quaternion Kahler manifold. But also there's another way to construct them. So you can think about acting on with the group structure on this almost complex of this bundle of almost complex structure. Okay, so you act on the endomorphism, and then this gives you some. So the orbit of one point will give you some submanifold, right? So in a good case, this will be a complex manifold. Right? So this gives you another way to construct twistor spaces. But this depends on the geometry, and you want to be this giving you things about the geometry of the manifolds. So somehow this is like the idea, right? So you have some geometry in the base, or some geometry in the total space. What can you say depending on the geometry on the space or on the total space, right? So somehow the idea is to so the dogma here is to change the problems on differential geometry to complex geometry on the twistor space.
My second question is, I think it's quicker to answer. So I know you said you didn't want to talk about the A tensor, O'Neill's, but I just have a very quick question. So when you proved your result that it was actually Kahler Einstein,
yes,
was it exactly that, or there was some sort of perturbation or modification of the metric? It was on the nose. It was also Einstein. Sorry, Kahler Einstein.
No, it
right.
was
so it was a big computation, and then you said, "Oh, it was also," or you had to do something else to the metric.
No. It was somehow the same metric. So I had the metric and the same metric, and it's quite like, I don't know. So somehow the coefficients of the stuff works like. Of course, for the Kahler metric. So how the Kahler metric works? So once you know the complex structure is. Once you know that the manifold is complex, this has nothing to do with a metric, right? But you can work with to scale the metric on the fibers. Once you have right, and then you can work with it. So this allows you to have some space to work with. So with some scale, the metric becomes scalar, right? That was somehow the case. This case, you can change it so that this is 0, right? Anyway, for proving that this scalar metric is a scalar metric, but also it's the same factor that you use that gives you the Einstein. So actually, in the classical case, you have two Einstein metrics. Okay, one is scalar and the other one is not. And for example, if you remember, I think I said this. So for example, here I'm changing the metric on the fiber to get an Scalar metric. And then I have also to change the complex structure. Would you have to define it by -j in the vertical space? So you have some scaling that helps you, but so to answer the question, is the same metric. That's why it was really like a really nice result, or at least for me, it was really nice. Even though if you see the coefficients they are really like not really natural, because somehow look at this, right? Somehow you want to so for example, yeah, you want this to be like the metric in the fiber, so you want the A. So this you want to have. Yeah, so there's many things. So somehow you want this to be like the metric in the base with a multiple, right? So that you get like G XY is the same with a factor here to the Ricci curvature. So somehow first you want this to be like the metric. So this is where the relation that I show you helps, and then you can rescale, but you also have the same here, right? So you want this to be a multiple of the metric, and then somehow with this factor and this factor and the factor that goes here, so somehow it all falls. So it's quite nice.
Okay, so I also wanted to ask about your theorem when the twistor space on the Ricci curvature, positive Ricci curvature, it's scalar. So how feasible it is to do it with non-negative Ricci curvature? Can you like somehow deform it, or?
No, it's really important to have like, well, as for this idea, it's really important to have positive too.
Right, but it's not enough, for example, to have positive Ricci curvature at like one point, and then try to somehow propagate this.
I don't know. I have to think about it. To deform, right?
Yeah.
Deform.
Yeah.
Yeah, I don't know, but I don't think so. But I don't know.
Okay, so thanks. Are there any more questions? Yeah. Okay, I'm on my way. Wait.
Okay, so I would like to ask you if you know about the obstruction theory for these even complex structures. Sorry, for these even Clifford structure.
The obstructions to.
Yeah, I mean, you say an even.
Yeah. Let me just remind. Do you mean like topological obstructions?
Yeah.
I don't have topological instructions, but there's some like geometric instructions that I don't recall now. But they're really somehow, well, at least for parallel, they're really restricted. But topological, no, I don't remember now what would be the topological obstruction to having this almost, well, even Clifford structure. No,
Yeah, actually, my question is more on the lines that if you know if there is some work done, because
no, there's no. I think there's no work done. because maybe for spin 7 there are, right?
Yeah.
And then you can think about more general stuff, right? But you have to think about that. This also should give you, for example, obstruction for having Kahler metrics or quaternion Hermitian metrics and so on. So this can be really interesting, but I think there's no.
Okay, thank you.
Okay, so if there are no more questions, let's thank Gerardo again.